Hello guys, welcome back to my channel. My name is Kenry Carty. Please remember to like and subscribe. Now today, we're going to be exploring the concept of integration by recognition. And on screen here, to start this off, we're going to look at what happens when we differentiate using the chain rule. And technically speaking, this would have been the shortcut of the chain rule. That says if we differentiate a function that has a power, we bring the power to the front, we subtract 1 from the power, and then we multiply by the differential of what is inside of the bracket, which would give me f prime of x. Good? But bear in mind that when doing the chain rule, we'd have also made a substitution to make the function simpler. So we're going to be looking at how we integrate using recognition by first making a substitution, going the long way, and then making a deduction as to what the shortcut will actually be. So let us say we are given a function of the form f of x to the n times f prime of x to integrate. This is a function I'm going to integrate. So we're going to start by making a substitution. Naturally, the problem I'm going to have here is with a function that has a power, which is f of x to the n. So we could say let u equal f of x. Now, of course, if I'm going to introduce u and I'm going to need du, which means I'm going to be integrating with respect to u. So it means that I'm going to have to differentiate this function. So we're going to have du over dx, which is going to be equal to f prime of x. Since we want to replace the dx, I'm going to have to transpose this formula for dx. So we could say that du equal f prime of x times dx, which means that du over f prime of x is equal to dx. So we can go back now and make our substitution. So it would actually become the integral of u to the n times f prime of x, which remains. And of course, I'm going to be replacing my dx with my du over f prime of x. Now look at what happens. My f prime of x down here would take out f prime of x up there. So this simply becomes the integral of u to the n du. And of course, we know exactly what to do here. When I integrate u to the n, with respect to u, we simply add 1 to the power. So I'm going to have u to the n plus 1 over n plus 1 plus c, which is your constant of integration. We can't leave it like this because bear in mind it was initially a function of x. So we're going to go back to replace the u. So let me just create some space here. So when I replace the u by f of x, I'm going to have f of x raised to the n plus 1 over n plus 1 plus my constant of integration, which is c. So let us summarize this here. What we're saying is that when we integrate f of x to the n times f prime of x dx, this is simply going to become f of x all raised to the n plus 1 over n plus 1 plus a constant of integration. This is what we would have actually derived. So for example, let us just write a simple function and apply the rule. So what if we have the integral, bracket, and let me put x squared plus 4 to the 6th power, and outside we have 2x dx. Now the first thing I would need to do is to state the form of recognition that I'm using here, which is this. So I would first have to write this back, which is the rule up here at the top that I'm using recognition. Or I could say by recognition. But we have to check the function to make sure that it does work. So we have a function to a power. The power of that function is 6. The function we have inside of the bracket is x squared plus 4. I have to check the function outside to ensure that that function is the differential of what I have inside of my bracket. Now when I differentiate x squared plus 4, I do indeed get 2x. So there is no need for any manipulation here. So we simply go ahead and we say we take the function, which is x squared plus 4. We add 1 to that power. The power of the bracket is 6. So it's going to become 7. We put that all over 7. And we add the constant of integration here. So we could actually write that as, and if you want to further manipulate that, you could actually write it as 1 over 7 x squared plus 4 all raised to the 7th power plus c, the constant of integration. Now what we're going to do, we're going to go it the long way and use a substitution and see if we actually get the same answer. So let me get some space here. So if we decide to use the long way, we have the function inside of the bracket raised to a power of 6 times 2x. What we're going to say is let u equal x squared plus 4. And as you know, if we're going to change it over to u, we're going to have du, or integrate with respect to u. So I'm going to have to differentiate this function. So du over dx. This is going to give me 2x. Now, I want du, so I'm going to have to transpose this function for dx. So we can say that du is equal to 2x dx. So du over 2x is equal to dx. Now we can sub this inside of the function. So it becomes the integral, the x squared plus 4 becomes u, so we have u to the 6 times 2x, and of course we replace the dx by du over 2x. Now look at what happens. 2x takes out that 2x there. So this becomes the integral of u to the 6 du. Of course, when I integrate that, I'm simply just going to have u to the 7 over 7 plus c. We don't stop there because our job was to integrate with respect to x. So we can now recall that u was equal to x squared plus 4. So this would actually become, and we could write that as 1 over 7, right? Well, let me go first with x squared plus 4. So I'm going to have x squared plus 4 to the 7 over 7 plus c, or 1 over 7 x squared plus 4 to the 7 plus c. And notice you get the very same answer. Now we have our next question on the page. Here we have 6x all over 3x squared plus 2 all squared with respect to x. But notice if you look at the denominator down there, what is inside of the bracket? 3x squared plus 2, the differential of that is actually 6x. But here's where a lot of persons normally go wrong. A lot of persons tend to forget that when you have something as a quotient, it can also be written as a product. So we could actually tidy this up by bringing up the denominator. So I'm going to have the integral of 3x squared plus 2 to the minus 2 times 6x dx. Now it looks exactly how I want it to apply recognition. Now, before we go into applying recognition, let us recall what recognition says. So we have it that the integral of f of x to the n times f prime of x dx would actually give me f of x to the n plus 1 over n plus 1 plus c. All right, this is what you're going to be using. So we're applying recognition. Now let us see if the function actually fits the criteria. For the function to fit the criteria, what I have outside, which is 6x, must be the differential of what I have inside of the bracket, which is 3x squared plus 2. It does matches that criteria. There's no need for any manipulation, so we go right ahead. So when we integrate that, we're going to add 1 to the power. So I'm going to have 3x squared plus 2. The power is negative 2. If we add 1 to negative 2, I'm going to get negative 1. And we divide by the new power, which is negative 1, plus the constant of integration, which is c. Now, of course, we can bring this negative 1 in the denominator out here and say negative of 3x squared plus 2 to the minus 1 plus c. And to refine this, we could take it back down in the denominator since the power of a bracket is negative. So I would have negative 1 all over 3x squared plus 2 plus c. And there goes my integral. And here we have a trig function that actually requires a similar application, because we know that if we differentiate tan x, we end up with sec squared x. Now, having the tan cube like that might be confusing for some persons. So you can always manipulate a function, write it to make yourself feel more comfortable. So I could write it as the integral of tan x I put the 3 up here, and then we have sec squared x dx. Now, once again, let us go ahead and recall the form of integration that we use in by recognition. So we know that the integral of f of x to the n times f prime of x dx is equal to f of x raised to the n plus 1 over n plus 1 plus your constant of integration. So how does that apply to this? Once again, we always say check to ensure that it fits the criteria. Inside of the bracket, we have tan x. The power n is 3, and of course the differential of tan x is sec squared x. So it does fit the criteria. So this is just going to become tan x raised to the 4th power over 4 plus c. And of course, you can always go back and refine it, right? So you're going to have tan to the 4x, which you can write, and you could probably put the 4 out here. So we have a quarter tan to the 4x plus the constant of integration. And there goes your answer. Here goes the next question. Now, sometimes the questions are not as refined as we want them to be. Because if I look inside of my bracket, we have 4x squared plus 5 raised to the 7. But what happens when you differentiate 4x squared plus 5? What you get is 8x. Now, outside of the bracket, I have just x. That is no problem, because bear in mind it is legal for you to multiply an integral by a constant. So we need to have an 8 in front of that x. So we're going to rewrite it. It becomes the integral of 4x squared plus 5 to the 7, and we multiply that by x, so we have 8x. However, we can't just multiply an expression by 8. Legally, we can multiply an expression by 1, which is a multiplicative identity. So if I multiply the x by 8, I'm going to have to multiply by 1/8 outside of the integral, because 1/8 times 8 is still 1. So the expression is not necessarily affected by that. Now, let us recall the recognition that we're using. So we know that the integral of f of x to the n times f prime of x dx is equal to f of x to the n plus 1 over n plus 1 plus a constant of integration. Good, so we're good to go. The 1/8 that is outside of the integral, we can ignore that for the time being. So that 1/8 comes back. So that's 1/8 there. Now, inside, everything is what we want it to be. The differential of a bracket is 8x, and we have that. So we simply take the function and we add 1 to its power. So I'm going to have 4x squared plus 5 to the 8 over 8 plus c. Simplifying this, we have 1/8 times that. So we could multiply the 8 by the 8, which would give us 1 over 64 times 4x squared plus 5 to the 8 plus the constant of integration. Now guys, recognition is not simply limited to the first form that we did. It can come in a lot of different forms. And here we have a next form where we have f prime of x trig f of x dx. When I put trig there, what I'm simply doing here is represent any trig function, for instance, sine, cos, sec squared, and so on. We just want to create a general expression. And to derive this form, we're also going to go ahead and use a substitution as well. So let us say let u equal f of x, which of course is a function that we differentiate. Now du over dx would be equal to f prime of x. Du would be equal to f prime of x dx, which would imply that dx is equal to du over f prime of x. So let us go ahead and rewrite this function. So the integrals would simply become the integral of f prime of x trig, and bear in mind that u is equal to f of x, so I'm going to have trig u times the dx, which is du over f prime of x. Now let us see what happens. The f prime of x here takes out f prime of x there. So all I really have here is the integral of trig u du, right? And then of course the integral of this is dependent on what the function is. If it is sine x, you know exactly what happens. We get negative cos. If it is cos x, we get negative sine. So let us throw in a function here just to clarify it. So what this is really saying here is that when we integrate f prime of x trig f of x dx, we simply just integrate trig u. We simply just integrate the function. So we ignore the f prime of x, we ignore f of x, and we think of it as just trig of x or trig of u, and we integrate that. All right. So to further clarify this, let us just throw in a simple function. So let us say we had the integral of f prime of x sine f of x dx. So let u equal f of x. All right. Now du over dx is going to be equal to f prime of x. And since we did the transposition already, let's go right into it. Dx is simply going to be du over f prime of x. So when I go back to the integral and I substitute it, I'm going to have the integral of f prime of x times the sine of u times du over f prime of x. Now, see what is going to happen here. This takes out that. So I'm going to be left with the integral of sine u du. Of course, when we integrate sine u, we end up with negative cos u plus c. But of course, recall that u was equal to f of x. So I'm going to have negative cos f of x plus the constant of integration, which is c. Let us put this inside of a question. So if I had the integral of x sine x squared dx, we know that the differential, so the function that you're assigning here is x squared. And when we differentiate x squared, we get 2x. So like previously, we can manipulate that. So I'm gonna have 2x there, sine of x squared dx. But of course, if we multiply by 2, we have to divide by 2. So I have a half outside. Now, inside, I have exactly what I want, 2x, which is differential of x squared. So we say you simply just ignore all those functions and you integrate the sine. When I integrate sine, I get negative cos. So we put back the half here, and I'm going to end up with negative cos. We put back the function, which is x squared there. So this becomes, and of course, plus your constant of integration, negative a half cos x squared plus c. And of course, you can always recall the form of recognition that we use in here. So let me just tag this in here, that the integral of f prime of x sine f of x dx is simply gonna give me negative cos f of x plus the constant of integration, which is c. Let us look at our next example. And we have 2x squared sec squared x cubed. And of course, the rule that we derive, as you have seen, we derive it generally for any trig function. So it will work for sec or any other function. But of course, we're going to have to do some cleaning up in this case. Now, the function that I have the sec of here is x cubed. However, when I differentiate x cubed, I get 3x squared. So we're going to have to tidy up this. The 2 there is not relevant, therefore, so that can go outside of the integral. So we have 2 integral of x squared sec squared x cubed dx. So incidentally, what I want is a 3x squared. So we can divide by 3, multiply by 3. So I can say, since we have 2 outside already, I'm going to have 2/3 the integral of 3x squared sec squared x cubed dx. Now before we get into it, let us create a general rule for this one here. What we're saying is that, let me change the color. is that the integral of f prime of x sec squared f of x dx. Of course, you know that when we integrate sec squared, so we're only paying attention to the sec squared, that when we integrate sec squared, we get tan. So all this becomes is tan f of x plus c. So let us translate that now over here. The 2/3 will remain outside, so I'm going to have a 2/3 out there. We're going to integrate the sec squared, which is going to give me tan, and the x cube, which is a function that I'm second come back. So I'm going to have tan x cube plus the constant of integration. All right, and never leave that off. Very important that we put it there. Now, mathematics can be very dynamic. So let us look at a second example. We have 2x over sec x squared. Now, of course, we have a trig function here, which is what is critical if you watch my previous video on the integration of trig functions involving identities. Because with the sec, we know that we can manipulate this. So let me go ahead and first I could say this becomes the integral of 2x times 1 over sec of x squared dx. And we know that 1 over sec is really cos. So it becomes the integral of 2x cos x squared dx. Now this looks exactly like how we want it, because the differential of x squared there is 2x. So we can create a little identity here to say that the integral of f prime of x cos f of x dx is equal to sine of f of x plus c. So when applied to that function, the function f of x there is x squared and f prime of x is 2x. So when I integrate that, I'm simply going to get sine of x squared plus c, which is the constant of integration. So that's the time trig functions come in, and you may have to apply a trig identity. It doesn't mean the function is more complex, it just means that we have to know our trigonometric identities.